Hello, my name is George Savic, and I am the author of the theory of quantum relativity. In my previous video, I gave you the quick and dirty introduction as to why there needs to be a theory of quantum relativity by showing you the contradiction that exists between special relativity and quantum mechanics. I hope that you made it through that experience in one piece.
Everything's perfectly all right now. We're fine. We're all fine here now. Thank you. How are you?
In my next video, I am going to finally reveal to you the complete theory of quantum relativity. But in this video, I am going to give you another quick and dirty example as to why there needs to be a theory of quantum relativity by showing you the contradiction that exists between special relativity and general relativity.
It's a trap!
Let's agree that in physics we have two inescapable laws, and that one of these laws is special relativity, which has two assumptions. And in this video, we will focus only on one of these two assumptions.
The speed of light in a vacuum is constant no matter who is doing the measurement and no matter what direction you are moving or how fast. You'll always get the same measurement for the speed of light. That's assumption one, which, by the way, experiment has shown to be true.
The other inescapable law of physics is general relativity, with a basic principle which states that a clock which is further away from the source of gravity will tick faster than a clock which is closer to the source of gravity.
Since gravity is weaker at altitude, while the test clock was up the mountain, time ticked faster. It's now 20 nanoseconds, 20 billionths of a second ahead of the sea level clock, just as general relativity predicts.
These two inescapable laws bring us to the thought experiment of the day. Let us imagine that we have two observers in two different frames of reference, and each observer has their own super accurate atomic clock. Let's agree that the moving observer is so close to the speed of light that he is experiencing 50% time dilation and 50% length contraction. Now, let us imagine that our two observers want to measure the speed of a particle of light as it passes over a ruler with a given length. And for the purpose of simplicity, let us agree that the length of this ruler is 300 million meters. We know that time ticks normally for the stationary observer, so we know that it should take 1 second for the particle of light to travel the length of the ruler. This gives the value of c for the speed of light relative to the stationary observer. We know that the moving observer is experiencing 50% time dilation. Therefore, the moving observer's clock will have ticked only half a second relative to the stationary observer's clock. So the moving observer should have the value of x for the speed of light. But from the moving observer's frame of reference, it is the other observer and the ruler that are moving. Because it is the ruler that is moving, therefore the ruler is experiencing the 50% length contraction. For this reason, the moving observer measures that it takes half a second for the particle of light to travel the full length of the ruler, which now appears to be half its original 300 million meter length. This gives the value of c for the speed of light relative to the moving observer. This is perfectly consistent with the assumption of special relativity, which states that all observers must measure the value of c for the speed of light.
If speed was constant for light, then space and time had to adjust themselves in order that speed stayed fixed.
Now, let us imagine that our two observers are both stationary near a source of gravity, something like the planet Earth. Let's also agree that our two observers are close enough together to agree on the length of the ruler, but far enough apart for their atomic clocks to tick at different rates. Again, for the sake of simplicity, we are going to exaggerate the time dilation that the clock, which is closer to the source of gravity, will experience. Let's agree that the clock below the ruler ticks 50% slower relative to the clock that is above the ruler. This way, when our two observers measure the speed of light relative to their atomic clocks, we find that the observer above the ruler measures 300 million meters over 1 second, which gives him the value of c for the speed of light. and we find that the observer below the ruler measures 300 million meters over half a second, which gives the observer below the ruler the value of x for the speed of light. Let us examine what just happened. Both of our observers agree on the length of the ruler. Therefore, both of the observers agree on the distance that light travels. Furthermore, both of the observers agree that time ticks slower for the clock that is closer to the source of gravity relative to the clock that is further away from the source of gravity. There is only one inescapable conclusion to all of this evidence. A basic principle of general relativity is directly contradicting the second assumption of special relativity.
It's not true! That's impossible!
Search your feelings, you know it to be true.
This leaves us with two options. One, either the second assumption of special relativity is not a law of physics, or two, we need another theory, a theory of quantum relativity, which can clearly explain how a law of physics can be circumvented without it being simultaneously contradicted.
So what I told you was true, from a certain point of view.
A certain point of view?
Luke, you're going to find that many of the truths we cling to depend greatly on our own point of view.